This equation may seem deceptively simple, yet this simplicity holds within it one of the most captivating mathematical mysteries of all time. Of course, for n equals 2, this is the famous Pythagoras equation. In the natural numbers, and throughout this video we'll only be talking about natural numbers, not only do we know that there exist infinitely many solutions, but we also have a general formula for generating all Pythagorean triplets. But what happens when n equals 3 or 4? One should think that we should be able to do something similar, but as you try, you realize that it is not as trivial as it seems, and indeed, it isn't. Known as Fermat's last theorem, it was stated by Fermat in 1637 that this equation has no solutions for any n greater than 2. For over 350 years, this problem has puzzled mathematicians. Before its proof in 1994, it was in the Guinness Book of World Records as the most difficult mathematical problem. Today, we will look at this equation, but with a little caveat. We shall look for solutions to the equation modulo primes, and as it turns out, this little addition changes the problem completely. But before we do that, we need to step back and travel to a very different world, the world of graphs. You are an engineer in the city of Island Polis. True to its name, the city is made up of a large group of islands. You've been given the task of constructing bridges across these islands. But alas, life is not so easy in the land of mathematical riddles. You have to construct a bridge across every pair of islands in the city. And if that wasn't a difficult task in itself, the city has an eccentric mayor. You see, the bridges come in 3 colors. The mayor hates triangles. He wants you to construct the bridges such that bridges of the same color never form a triangle. Cursing him under your breath, you begin laying out the plan. But you notice something very weird. You try for hours, but in vain. Every plan you draw up always has a triangle. Having studied discrete math in college, you recall a problem that you saw in one of your very first classes. Show that any party with 6 people will contain a group of 3 mutual friends or 3 mutual strangers. The proof of it goes something like this. You model the situation as a graph, letting blue edges connect friends and red edges connect strangers. Since you have 5 edges going out of each vertex, there must be at least 3 edges of the same color among these. Let's assume they're red for this vertex. Now, none of these 3 vertices at the bottom can have a red edge in common, because if they did, we would get a red triangle and we're done. But that means all 3 of them are joined by blue edges, and there you go. We have a blue triangle now. Let's go through the proof once again, seeing why it works. If you were to color a graph with just one color, you would only need 3 vertices to form a triangle. And so, when you have just enough vertices in a graph so that you have at least 3 edges of the same color going out of each vertex, you're guaranteed to get a triangle. You try to extend this proof to the 3-color version and hope that that might help solve your problem. We know that 6 vertices, when colored with just 2 colors, are guaranteed to give us a triangle. So if we have enough vertices so that there are at least 6 edges of the same color going out of each vertex, we are done. In order to not have 6 edges of the same color, the maximum number of edges you can have going out of a vertex is 15, 5 of each color. So if there are at least 16 edges going out of each vertex, that is, if we have at least 17 vertices in our graph, we are always guaranteed to get a monochromatic triangle when we color the graph with 3 colors. We can extend what we just saw to 4 or 5 or any number of finite colors. That means no matter how many colors we have, there always exists a number n such that when we color the complete graph on n vertices with these colors, we are guaranteed to get a monochromatic triangle. In fact, this is just a special case of a more general theorem called Ramsey's theorem. As we shall see later, this will help us answer a very important question. But before that, we need to take yet another detour, this time to the world of groups. Let's look at the permutations of these 4 objects. I've labeled them so it's easier on our minds, but they're identical. Any permutation of these objects leaves them unchanged, that is, exactly as they were before. The idea of a group arises naturally whenever we have symmetries like this. We say that these actions that leave an object unchanged, in this case our set of 4 points, form a group. This gets really interesting when we start looking at how these actions interact with each other. For instance, when you compose two of these actions, two of these permutations, you get another permutation. When we study these actions and how they interact with each other, we start observing some really interesting properties. For instance, if you were to pick any of these permutations and applied it over and over 24 times, you would get back the initial order you started with. In order to understand why this happens, we need to take a break from these fancy animations and learn a few things about groups. If you search online for the definition of a group, you might find something like this. So a group is a set G with an operation, let's call it dot, that satisfies these following four properties. So I'll just list them quickly out here. The first is closure. It just says that the group is closed under this operation. So if A belongs to G, B belongs to G, then AB belongs to G. 2 is associativity, which just says that it doesn't matter where you put the brackets. So when you're doing something like this, you can write such expressions without any brackets. 3 is there exists this identity element in the group. So E belongs to G such that and finally there exists an inverse. For all A belongs to G, so let me just that there exists A inverse such that this is true. Alright, let's just look at some examples of groups. So one very obvious example of a group is a set of all integers under addition. So you add any two integers, this is also an integer, and you can define 0 as the identity and minus x as the inverse of x. Now one thing you should notice here is that nowhere have I mentioned that this operation is commutative, and it generally isn't, but for the rest of this video we will only be dealing with commutative groups. So they are also called abelian groups, just to introduce some jargon. Let's go ahead and look at another example of a group. This is ZP modulo P. Now this also forms a group because you add any two elements, you get another element from ZP, and then you can do the same thing again. So you call 0 the identity, and then the class representing minus x or P minus x, that is the inverse of x. Now what about this? A set of all integers, but instead of looking at addition, we look at multiplication. So again, A times B is still an element of Z, but does it satisfy the property of an inverse? So first of all, when I say Z here, I mean Z without 0, because obviously 0 you multiply with anything, you just get 0, and in a multiplicative group the identity would be 1. This is the identity. And it is obvious that the inverse doesn't always exist, right? So for instance, the inverse of 2 would be 1 by 2, but then this does not belong to Z. So Z under the multiplication operation does not form a group. And in fact, if you just added the inverses and looked at the rational numbers instead, they would actually form a group. So this is not a group. Now what about this? ZP under the multiplication operation. Now again, when I say ZP here, I say ZP excluding 0, because it doesn't make sense to have 0 under the multiplication operation. 0 doesn't have an inverse. So here again, closure, identity, all that stuff is satisfied. So we really just need to check if there is inverse, right? If the inverse of every element exists. Now what does inverse even mean in ZP? So the inverse in ZP would mean that x is the inverse of a, then ax equal to 1, right? And that means ax should be congruent to 1 mod p. And if you remember, we proved that in class that for every a there exists an x such that this is true, and we actually did it for the more general case where we had n instead of p, and we showed that this is true if and only if the a and n are co-prime. Now since p is a prime, every a is co-prime to p, so that means the inverse of every element exists. So this actually does form a group. So from this we can see that the inverse does exist. And so this is a group. And from now on, whenever I refer to this, I shall refer to it as this. So now let's go ahead and define something very natural that comes up when we are talking about groups, and that is the idea of a subgroup. Sorry about this. Okay. So a subgroup, it's pretty self-evident, right? So it's just a subset of the group that also forms a group. So it is also closed under the same operation, and the identity and inverse and all that stuff exists. Now the subgroups have some really interesting properties when we are dealing with finite groups. And by finite groups, I mean groups that have a finite number of elements. So before we go ahead, let's just define some more jargon. So if I say, I shall use this, and I will call this the order of G, and this is the number of elements in G. So now we are just looking at groups that are finite. Just give me a moment. Alright. So when we are let me just write this down again. So let's say you have a group G, so that is some elements in so on, and you have H is a subgroup of G. Let's just use better notation and call these elements G1, G2 and so on. And let's say H is this. Have H1, H2 and so on. Now, something really interesting we notice about subgroups. So let's just look at some examples of subgroups. So yeah, I just want to talk about examples so that the idea of a subgroup is really clear. So one thing you can consider as a subgroup of, let's say, Z is a set of all even integers. So this would be -2, 0, 2 and so on. And you can clearly check that this satisfies all the properties of a group. And similarly you can talk about 3Z, 4Z and so on. But these are subgroups of an infinite group, right? Because Z has infinite elements. But consider, now let's get back to abstract groups again. So consider this group and this subgroup, let's say 2 and so on. Something really interesting we notice is that the order of this subgroup always divides the order of the group. The order of any subgroup of this group will always divide the order of this group. Now in order to prove this, we shall have to introduce some more jargon. So let's introduce the idea of cosets. Now whenever you have a subgroup of G, you can define these cosets of this group. So let's say GH, where you pick an element that is not in the subgroup. So you pick an element of G that is not in the subgroup, and then you multiply it with every element of the subgroup. So on. And now you can see this set will also have the same size as this set, because if the size of this set were to be less, then that would mean this is equal to this. But since we know that you can multiply by the inverse on both sides, this would imply that H1 equals H2. So basically this implies that corresponding to every element in this subgroup, you have an element in this coset. So the size of this is equal to this, and this coset itself would be something like, let's say it would have some elements, let's say A1, A2 and so on, and you can pick any of these elements. Even G is one of those elements. You can pick any of these elements to represent this coset. Now what do I mean by that? To use some more jargon, we say that these cosets form equivalence classes. So if you consider this relation G1 related to G2, if G1H, the coset of G1, equal to G2H, you can easily see that this is an equivalence relation. I leave that as an exercise to you. But what that tells us is that you can pick any of the elements in the coset to represent this coset. So this could equivalently be written as A1H or A2H and so on. Now the next thing we need to look at is, now let's say you have all the cosets. So let's just write them down. Let's say you have A1 AH, or let me use different notation. So let's say you have AH, BH and so on, the cosets of H. Something very interesting that we need to note here is that every element belongs to only one coset. So to put it more rigorously, if the intersection of, let's say, one of the cosets, I pick one of the cosets, and the intersection of it with another coset, it must be empty, and if it is not empty, it implies that they are equal. So again, this is fairly trivial to prove. So in order to prove that A equals B, you just have to prove that A is a subset of B and B is a subset of A. And again, this is something very trivial. You can just assume that the intersection is not empty and then show this, and you're done. But then what this tells us is that H partitions, okay? So H partitions G into these equivalence classes, right? And we just saw that each has the same size as H. And so what that means is the size of G would be the size of H plus the size of AH plus the size of BH, which means G equals H times N, where N is the number of cosets. So there you go. This is one of the most fundamental theorems in group theory. It's called Lagrange's theorem. Now let's go ahead and learn even more jargon, right? So let's talk about the order of an element. No. Order of an element in a group. Let's say I have G and this is more G. So basically this is the smallest number such that G raised to that is the identity. So first of all, we need to show that there always exists a number like this, and that is pretty simple, right? So you just consider this set. So you have E, G, G square and so on up to G power n minus 1, let's say, where n is the order of the group. The group okay, let me just replace this. You'll quickly see why. So now either two of these elements are equal, in which case you get G power m equals G power n. Let's assume m greater than n. In that case you're done. So you get G power m minus n equals E. Now if you find no two such elements, then that means all of these elements are distinct. But then that means you get the entire group again, because the size of this set is equal to the order of the group. So that means G power n itself would be equal to the identity. So otherwise G power n is equal to the identity. Alright. So now let k be the order of, let k be the order of A. Again this belongs to G. So then consider this set. So identity A square, so on up to A to the k minus 1. Now, this also forms a group. Now, why? It's pretty clear to see. It is closed under the group operation, because let's say you multiply A power m times A power n, you get A power m plus n. But then if this is greater than k, we know that this is we know that A power k is 0. So if this is equal to, let's say, A power kq plus r, where m plus n equals kq plus r, then this would be A power r, because A power k is the identity. So that means this is closed under the group operation. And the inverse also exists, right? Because using the fact that A power k is the identity, you can construct the inverse of every element. So that means this is a group. And from now on we shall call this the group generated by A. Alright, so it's pretty clear to see that the group generated by any element, it is a subgroup of G, and it might be G itself too. So now let's just go back to what we have learnt in class and look at Fermat's little theorem. So Fermat's little theorem, it says A power p minus 1 congruent to 1 mod p. And if you look at this from a group theory perspective, this should be an obvious fact, because every element, now if let k be the order of A again, then this subgroup generated by A also has order k. But this implies that k must divide the order of the group from what we proved earlier. So what that implies is that if a power k is equal to e, then a power n should also be equal to e, where this is the order of the group, because k divides n, so you can write n as some m times k, and this would be equal to a power k times m is equal to e. So you see that every element of a group satisfies this property. So let me just put that down in a box because it's really important. Every element of a group satisfies this property, and Fermat's Riddle theorem is just a generalization of that, because if you look at this group, its order is actually p minus 1 because it does not contain 0. And so this is just one example that shows us the power of dealing with groups abstractly. Alright. So let's just go ahead and introduce this final bit of jargon that you need to know, and that is the idea of a group homomorphism. A group homomorphism. If you recall from linear algebra, this is very similar to a linear map. So what a group homomorphism essentially is it's a function from a group to another group such that it preserves the structure of the group. So basically f of g1 times f of g2 equals this, and so you can obviously see that f of the identity of this group should be equal to the identity of H, and the inverse of G lands on the inverse of whatever the image of G is, and so on. So it has all these nice properties. Now let's just go ahead and look at an example of a homomorphism. So consider this, f from z to z, f of x equal to 2x. Now obviously f of 0 lands on 0, and then you have f of 1 plus 2 equals 2 times 1 plus 2 times 2, which is equal to f of 1 plus f of 2, and so on. So this is a homomorphism, and let's, using this example itself, let's go ahead and define a little bit more of jargon. So we call the kernel of a homomorphism of f as a set of all elements, so x, such that f of x equals the identity. So in this case it would be 0, so in general it's the identity. And now you clearly see that In our map, the kernel is just 0. Yeah, so it's very trivial. But now let's go ahead and look at the kernel of a very general homomorphism. F of G to H again, where G and H are subgroups, and let's look at the kernel of G again. So let's just write it out down again. Oh, sorry, I meant the kernel of F X such that F of X equals the identity in H, right? So one obvious thing that we can see is the identity also belongs to the kernel. Let's just call this K. Now if you look at the kernel closely, you notice something, right? So if F of K1 equals E and F of K2 also equals E, so these are two elements from the kernel, then F of K1 times K2 from the definition of a homomorphism should also equal E. So what that tells us is the kernel is actually a subgroup of G. So this is a subgroup of G. And so like we did earlier, we can talk about the cosets of the kernel again. Now one thing I forgot to mention earlier, and something that's really important, is that the cosets themselves form a group. Now that is really evident if we look at it with an example. So let me just write that down here. Cosets form a group. So if you have G and you have H, then you have all these elements H, A1H, A2H, and so on. Now all of these form a group, and to define how the operation works in this group, it's pretty natural. So what you do is you define this to be the identity of this new group, and you basically say that A1H times A2H can be defined as A1 A2H, and similarly you can define the inverse of A1H as A1 inverse times H. And it's a really trivial task to verify that this is indeed a group, and I leave that to you as an exercise. And this group has a special name. It's called the quotient group of whatever subgroup we used to make the quotients. So it is the quotient group of H, and it is denoted by G by H, because in some sense you got this group by partitioning G into equivalence classes. Now similarly, if you look at the subgroup, the quotient group of K, so the kernel of the homomorphism, let's get back to where we started. So if you look at this group, then you get the equivalence classes of F. In other words, when you look at this group, each set contains all the elements that have the same image in the homomorphism F. So let's just go ahead and see what that means. So let's say you have K equals K1, K2 and so on, and all the cosets would be of this form. So let's say A1 times K, that's equal to A1 K1, A1 K2 and so on. Now you pick any two elements from this set. So you have F of A1 K1 is equal to F of A1 times F of K1, which is equal to F of A1, because this is the identity. And similarly, if you look at F of A1 K2, F of A1 K3 and so on, they all give you the same value. So in some sense, this quotient group of the kernel gives you the equivalence classes of F. And that is basically it. So that's almost everything you need to understand about groups in order to understand the rest of what is to come in the video. And although this might have been quite a lot, considering we covered it in very little time, you can always feel free to pause and look these things up, check the proofs for yourself, and come back to the video to watch the rest of it. Okay, so we're finally ready to tackle this equation again. To begin with, we need to answer a few questions about nth powers in CP. For starters, how many nth powers do we even have? It turns out that what we have learnt about group theory is going to help us answer this question. Consider this homomorphism that takes in every element and rises it to the power of n. Now, since each equivalence class of this homomorphism represents an nth power, the question we want to answer essentially becomes a question of counting the number of equivalence classes. If you remember from what we discussed about equivalence classes, it is the quotient group of the kernel. So what's the kernel here? It's a set of all roots of x to the n minus 1. Here, we'll have to make use of a result that is state without proof. A polynomial of degree n in GP has at most n distinct roots. The proof is very similar to that of the proof for polynomials over real numbers, and is just a consequence of the fact that both real numbers and GP form a similar algebraic structure called a field. Consider for a moment the group formed by the equivalence classes of F. Since each class represents an nth power, this is the same as the subgroup of all nth powers. By Lagrange's theorem, we know that the order of G divided by the order of H must give us the order of the kernel. So the order of the quotient group of H is at most n. So finally, to restate what we have taken away from all of this, there are at most n cosets of H, and they all look like this. The important thing is that none of this depended on what GP was. So this is true for any prime number P, no matter how large it is. In my opinion, what is to follow is the most beautiful part of this video. I mean, the first time I saw this, I couldn't even believe what I saw. Let's associate each of these cosets with a color of our choice and construct a graph with p minus 1 vertices, each labeled with a number from 1 to p minus 1. Join every pair of vertices with an edge that is colored by the color of their difference, that is, the color of the coset to which the difference of the numbers belongs to. Recall from what we showed earlier in the video. If we make p large enough, we're guaranteed to get a monochromatic triangle. Consider these three vertices, I less than j less than k, forming such a triangle. Their edges are labeled with the colors of j minus I, k minus j and k minus I. But we have j minus I and k minus j adding up to k minus I. And since the three of them belong to the same coset, they're of the form ax to the n, ay to the n and az to the n for some a, x, y and z. And yep, that brings us back to where we started. X to the n plus y to the n equals z to the n. But what does all of this even mean? And this tells us that for primes large enough, this equation always has solutions in GP for any n.